So, what are we going to do today? We're going to discuss interference. So, in the previous classes, we introduced traveling waves. So now we know how to analyze traveling waves, right? So how to get all its properties. So pretty much now we can say that we know how to deal with one traveling wave. So next step, logically, what should be the next step? Increase number of waves. What if we have two waves overlapping, right? Interacting somehow? What are we going to get in these situations, right? And we're going to simplify our life to some extent. We're going to assume that these two waves which are interacting, they are identical. So what do I mean by identical? So they have exactly the same amplitude. They have exactly the same time behavior, for example, exactly the same period, and they behave in exactly the same way in space. So they have the same wavelength. So two identical waves. But of course, we're going to assume that they are produced by two different sources, right? Okay, so which situations are possible? And yeah, of course, we're going to assume that those waves, traveling waves, are one-dimensional. So they propagate along the same line. So what is possible in this case? So if we have a chord, typical example, right? And let's assume that there are two waves propagating on this chord. So we can create these two situations. For example, one source is over there, and one source is over there. Of course, in this case, you will have two traveling waves propagating towards each other. And of course, they're going to interact. In these situations, you're going to get standing waves. You're going to discuss standing waves in Physics 3. I stopped discussing it in Physics 2. So it's one case. So the second situation, what if you have two identical waves, but now propagating in the same direction? But again, sources are different. For example, one source is here, and the second source is here on the chord. And then you have two traveling waves propagating that way. Of course, over here, they're going to interact. Or we can say they interfere. All right? Okay, so we're going to discuss... Don't scare me, guys. Somebody's mic is on. Right? So they're going to interfere. So we need to discuss this situation. Right? So first, conceptually, and then actually mathematically. And we're going to do a little bit of derivation because the equation, the conditions which we're going to get, they're not something fundamental. They're not like Faraday's law, Coulomb's law. No, this stuff is derived and it's not that complicated. So we're going to get through some derivations. Okay, so but first let's discuss conceptually. So let's assume that we have two waves. You see, blue wave and green wave. And again, they're identical, the same amplitude, the same frequency, the same wavelengths. And they have, of course, the same, as a result, they have the same speed. And again, you see they're propagating in the same direction. So it's a first special situation in which we are interested. All right, so in this case, what will be the resultant wave? Of course, these guys. You see, we have crest over crest, trough, green trough over blue trough, and again crest over crest, trough over trough, and they travel with the same speed that way. So this configuration overlapping is going to be there all the time, right? So now if we try to imagine the resultant wave, it will be something like this, a wave with a doubled amplitude. So you will get something like this, right? And this wave is going to travel also with the same speed, right? So this case, when amplitude of the resultant wave is doubled, is called constructive interference. So this is the special case of constructive interference. How should I write? Probably I will write underneath. So I'm going to use symbol C, and it's a case of constructive interference. Very often we're interested in this situation. So if you create conditions for for these two waves in such a way so there is a full overlapping, we're going to get constructive interference. Then, second situation, what if you create conditions for the blue wave and green wave so that they interfere in this way? What we have? We have crest, blue crest over green trough, then blue trough over green crest, and so on. Crest over trough, trough over crest all the time. So again, they are going to interact, they are going to interfere. But of course, in this case, they're going to kill each other. There will be complete destructive interaction, right? So the resultant wave is going to be just undisturbed medium. This will be the resultant wave, right? So this case is called destructive interference. And we're going to use a symbol D. I should have left some space. D, right? Destructive interference. Destructive interference. Okay, I will skip word interference. All right? Okay, so in this class, and of course, it's also possible something in between. If you, for example, take this green wave, slightly shift to the right. Of course, you're not going to get neither this case nor that case. You will have something in between, right? So, but we most of the time we're interested in this limit situation and in that limit situation. Right? So that's conceptual discussion, and now let's get into mathematics and get this situation and that situation mathematically. Right? And again, derivation is not that complicated, and you should be able to follow. Okay, so let's assume. First let me write down that. Now I will put a new bullet, and right, let's get into mathematics. So imagine this situation. We have two speakers. Yeah, nature of waves can be any. Like you can have waves on a chord. You can have two acoustic waves propagating in the same direction, or two electromagnetic waves, I know, radio waves, right? So this can be applied. So let's assume that we have acoustic waves. We have speaker number one, you see, and speaker number two. They generate two waves, you see, green and blue. And of course, in this region, they are going to interact, right? So, so let's imagine that I stand over there at point P and listen to the net, of course, net resultant wave. So I want to get conditions under which I'm going to hear over there very loud sound, constructive interference, and I want to get conditions where I'm going to listen, when I'm going to hear nothing, destructive interference at that point P, right? So that's the goal. Let's find the conditions that we have to impose on these two waves in order to have very loud sound over there at that point and nothing. Okay, so let's do it. Yeah, let's assume that this point P is at the distance x1 from the first source and at the distance x2 from the second source. Right, so this is physical situation. And now let's get into mathematics. So first of all, let's write down traveling wave equation for the first wave and for the second wave from the previous class. You remember those equations, right? So, probably, yeah, I should be able to fit y1 at x1 and t. Pretty much, it's a disturbance created by the first wave at this point P, so at the distance x1. That's why I put x1 instead of just x in general, because I'm interested in that particular point. So that's why I sort of fixed x1, fixed x, and that is x1. And of course I can write, okay, I'm going to use small a as an amplitude. You will see in a few minutes why. It's not a crime. All right, so a, and then sine kx1 minus omega t. Okay, I should have probably started writing slightly lower. And plus initial phase x1 0. Oh, phi 1, 0. Phi 1, 0. Right? So that's the disturbance created at this point by the first source. Now let's write the same for the second source. Y2, x2t. So now, of course, x2 because the point P is at the distance x2 from the second source. So I'm just writing the traveling wave equation for the second wave. The same amplitude A, you see, and the same x and time dependence. So, but now kx2 minus omega t and plus phi 2, 0. So these two waves interfere. So now it means what? We just need to add them, right? We just need to add them. So the resultant wave, all right, so let's say y equals y1 plus y2. Okay, so you see, amplitude can be factored out. And then we will have to add two sign functions. High school stuff, you remember, trig identity, I prepared in advance. If you want to add two sign function. Before we go into this addition, right? So you remember how we called this construction in the bracket. It's a phase of the wave, right? So this is, or we can call it a phi 2, and this phase of the first wave, phi 1. Right? You remember in the previous class I mentioned this, but now since I'm going to use it, it's better to remind you. So this is the whole thing, this thing in the bracket. All these terms are called the phase of the first wave, and this is phase of the second wave. Okay, so now we have a sine phi 1 and a sine phi 2. And so now, yeah, we need to add two sine functions. Again, trig identity from high school, you should remember. 2 cosine phi 2 minus phi 1 divided by 2 times sine phi 2 plus phi 1 divided by 2. Right? Okay, so now let's use it over here. So we're going to add these two sine functions. A and 2 can be factored out immediately. So we will have 2a. Then this cosine phi 2 minus phi 1. Again, it's a phi 2 minus phi 1. Let me just introduce delta phi. I'm not going to dive into this delta phi for now. I'm going to do it in a few minutes. So let me write, so it's a cosine delta phi over 2. Let me put it in a bracket. And now this sine function, sine phi 2 plus phi 1. Sine, and open the bracket, phi 2 plus phi 1. So it's this plus that. So we have k x2 plus kx1 divided by 2. K and over 2 can be factored out. So we'll have k x2 plus x1 divided by 2. It looks like I will have to move to that wide side of the whiteboard. Then, again, I'm still dealing with this. So what's next? Minus omega t and minus omega t. So it will be minus 2 omega t divided by 2. It will be minus omega t. Minus omega t. And then plus. Okay, I will have to move. Sorry. So the second, the next term are these initial phases, phi 2, 0 and phi 1, 0. This plus this divided by 2. Right, so phi 2, 0 plus phi 1, 0 divided by 2. And I can close my square bracket. Okay, so now let's denote this construction. Phi 1 plus phi, x2 plus x1 over 2. Let's call it x average. Because what is this? It's this distance x1 plus x2 divided by 2. It's the average distance from both of these sources to the point P. So let's just call it x average. X and subscript A, V, G. And this, let's call it phi. I think where I put subscript, just a second, I just want to follow my notes. Okay, average subscript phi average and 0 upper script. Okay, so now with these notations, let me rewrite our resultant wave. Y equals 2a cosine delta phi over 2, and then sine k x average minus omega t and plus phi average 0. Okay, so that's the net wave. That's the resultant wave, right? And so now, under certain conditions, of course, we're getting this constructive interference. Basically, this represents this red wave. And under certain conditions, from here, we're supposed to get this straight line, no disturbance, right? It all here. And look, what we got here. Is it a traveling wave? Yes, it is. Because look, we still have a traveling wave equation. We have sine kx. Okay, now we have some kind of average, but still it's x. Then minus omega t, so we have time dependence, and we have some new initial phase. But still, it is a traveling wave equation, but with reasonably complicated amplitude. So this, we can call it, for example, like, let me label it as A capital. That's why over here I used a small, so that I can save A capital for the amplitude of the resultant wave. Right? So basically it's a traveling wave equation, traveling wave, but with complicated amplitude, which depends on the phase difference between this wave and that wave. So inside of this, there are lots of information. So basically now out of this, first we need to get this condition when amplitude is maximum, right? And then out of this, we need to get this situation when amplitude is 0, right? So now let's get these two situations in which we're interested. Right? So which way should I write it? No, just probably I will also write, so it's amplitude. Amplitude of the resultant wave. And so now maximum. Let's try to get this situation, constructive interference. So what's the maximum value of this amplitude? And when it happens? Of course, maximum amplitude is 2a, because cosine function, maximum value plus 1 and minus 1. All right? When cosine equals plus minus 1, we're going to have maximum amplitude. This situation. This amplitude cannot be larger than 2a, because you remember cosine function between plus 1 and minus 1. So a maximum equals to 2a when cosine of delta phi over 2 equals to what? Cosine function, you remember when it reaches, okay, so let me first write plus minus 1, when it's equal to plus minus 1. So when cosine function is plus minus 1, it's 0. Cosine function, you remember cosine function 0, then pi, 2 pi, 3 pi, 4 pi, 5 pi, and so on, right? So integer number of pi's. Okay, so it happens when this equal to m times pi, where m is an integer, right? You remember cosine function. So from here, as a result, so delta phi over 2 equals m pi. So as a result, we can write that delta phi equals to m times 2 pi, where m is an integer, 0, 1, 2, and so on. So this is condition for constructive interference. Okay, let me put over here. So this is a condition for constructive interference. When the phase difference between this wave and that wave, because that's what delta phi is. equals to integer number of 2 pi's. Right? Okay, these 2 appeared from there because that's sometimes students get confused where this 2 came from. From here, delta phi over 2. Okay, so with this condition, we can get constructive interference. But it's not the end of the story because inside of delta phi, there are tons of information. So next step, we will have to dive into this delta phi, revealing the whole truth, right? And nothing but the truth. So for now, I will just frame it lightly with green because it's not the final result. Now, let's get this situation. Condition to get that situation. So over there, we have minimum amplitude. So A minimum, of course, 0. It happens when cosine equals to 0, when this cosine equals to 0. So when cosine of delta phi over 2 equals to 0. So when is cosine 0? Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, right? So that happens when this delta phi over 2 equals to m plus 1/2 times pi. So again, when m equals 0, you will get pi over 2. When m equals 1, you will get 3 pi over 2. When m equals 2, you will get 5 pi over 2, and so on. So yes, it will work. Okay, again, m is an integer, right? And of course, what we want to get? We want to get delta phi from here, right? So these 2 will go to over there. So as a result, we're getting the conditions. So delta, you know what, let me move it slightly this way. So delta phi equals to m plus 1 over 2 times 2 pi. And so this is a condition for destructive interference. Again, m is the same integer, 0, 1, 2, and so on. Okay, again, I can frame it, but lightly, because it's not the final result. So now, again, what is inside of delta phi? Delta phi, it's this phi 2, which is kx2 minus omega t plus phi naught. And phi 1, also that. So let's actually subtract these phases and reveal the whole, the whole set of information. Right? Okay, so now let me check if I mentioned everything. Yes, so we got these 2 conditions, and now, so now let's look inside of delta phi, inside of this delta phi, inside, of course, this delta phi. Right? Okay, so we see what is delta phi. Right, so delta phi, which is phi 2 minus phi 1 equals, again, this is phi 2, this is phi 1. Okay, so let's subtract. Or you know what, I will just rewrite so that it will be easier to understand. Kx2 minus omega t plus phi 2, 0. I just rewrote this. And minus this. Minus kx1 minus omega t plus phi 1, 0. Okay, so let's subtract them. All right, so k x2 minus kx1. It will be k x2 minus x1. So let's call it delta x, k times delta x. So it will be k times delta x. So it's this term and that term. Right. Then minus omega t minus omega t. We will get minus omega t plus omega t. So omega t will disappear. Then phi 2, 0 minus phi 1, 0. So should I write it? So okay, I need to start the camera just a second. So phi 2, 0 minus phi 1, 0. Let's call it, let's label it this way. Delta phi sub 0. inherent phase difference. I will write the name for this. So now the last step. K, what is K? It's a wave number, 2 pi over lambda. And so we're getting the final condition that we want to get, right? So instead of this, it's a 2 pi over lambda times delta x plus delta phi naught. And this, for constructive interference, must be equal to m times 2 pi. And for destructive interference, it must be equal to m plus 1 over 2 times 2 pi. So the final condition. So let me write this, rewrite 2 pi over lambda times delta x plus delta phi naught equals. So for constructive interference, where is my constructive here? M times 2 pi. So it must be equal to m times 2 pi for constructive interference. And this must be equal to m plus 1 over 2 times 2 pi for destructive interference. M plus 1 over 2 times 2 pi for a destructive interference. So that's the final result. That's the conditions. These are conditions. So now let's label. So delta x. Basically, what is delta x? It's a x2 minus x1. It's that additional distance that the second wave has to travel relative to the first wave. The path length difference. Delta x is called the path length difference. So let me write over here. So delta x is path, length difference. And what is delta phi naught? Delta phi naught, again, what is delta phi naught? It's the initial phase of the second wave minus initial phase of the first wave. It's called the inherent phase difference. Inherent phase difference. Okay, so now every time, if you want to analyze interference for this case and that case to get constructive and destructive interference, what do you have to do? You have some two sources. Find the different distance between these sources to get path length difference. Then analyze, we'll see how, the initial phases, take their difference, find inherent phase difference, plug them here, and see after adding, what are you going to get? Are you going to get m times 2 pi, integer number of 2 pi's, or m plus 1 over 2 times 2 pi? Right? Again, I should have written probably that m is an integer. M is 0, 1, 2, 3, and so on, integer. Right? So, at the end, all the time when we're going to solve problems, we're going to use this condition. But now let's make one step to the side. No. Before making the step, we need to discuss the how can we find inherent phase difference? Because finding delta x, usually students don't have troubles. We need to discuss the inherent phase difference because that's where the student's not very comfortable. But again, the meaning is just phi 20 minus phi 10, difference between the initial phases. Most of the time in the problems, we're going to see three situations for delta phi naught. Which are those? You know, it's time to erase this appendix. Okay, you have it. Now we don't have it. So delta phi naught. So let's imagine, okay, maybe I will write delta phi naught and put a question mark. So situations. First, let's assume that we have a couple of speakers, right? Let's say this situation. Right. speaker number 1 and speaker number 2 generating, let's assume this situation. They generate these waves. Two sine waves. Basically, it's a snapshot graph at t equals 0. So let's look at, okay, it's a snapshot. Snapshot graphs, and let's say at t equals 0. So this is first situation. So we have what? Sine function, sine function. So according to this equation, initial phase for the first source is 0. Initial phase for the second source is also 0 over here, right? So over here it's phi 1, 0 equals 0. Phi 2, 0 equals 0. As a result, the inherent phase difference is 0. Right? In simpler words, look, since we have complete overlapping of two waves, you don't have to shift, for example, second wave by any distance, right, in order to overlap with the second wave. So in this case, we can say that inherent phase difference is 0. And these two sources are called in phase. So if a problem says that, let's say we have two acoustic waves, two sources in phase. Okay, so immediately you should be able to, it should trigger your brain. So in phase, it means that inherent phase difference is 0. Right? Of course, you can say, you can have, for example, here cosine function and cosine function. In that case, again, they will be completely overlapped, and inherent phase difference is 0. So these are called in phase. So let me check. In phase or sources identical. So these sources identical or in phase. Right. Okay, so if the problem says you have two identical sources, it should immediately trigger your brain. Inherent phase difference is 0. So that's the first situation. Now the second situation. What if we have, again, two speakers, right? Two speakers, but now let's assume that they generate these waves. The first speaker generates still sine function, right? Maybe I should write even here. So it's a sine, and this is also sine function. But now we have here sine function, but the second source will give us minus sine function. Again, it's a snapshot graph at the initial moment of time. So you see we have sine function, and now over here we have minus sine. So you see the first wave goes up immediately, the second wave goes down immediately, right, after the source. So we have sine and minus sine. So what will be the initial phase of the first source? 0. Of the second source is pi. So if you take the difference, the inherent phase difference, delta phi naught, in this case, is pi. These two sources are out of phase. Again, if the problem says we have two out-of-phase sources, it should trigger your brain immediately. Out of phase, it means inherent phase difference is pi. So one generates sine function, the second generates minus sine function at the initial moment of time. Right? So I can write in this case delta phi naught equals 2 pi. And as I said, out of phase. Let me check if I haven't mentioned something. Okay, out of phase. Out of phase. Right. Probably I should even frame. So in this case, it's a delta phi naught. In this case, delta phi naught is pi. In the last situation, occasionally we might see that what if the first source and the second source generates these waves? First source still sine function, You see, still immediately it goes up from the source. But the second, what if the second give us this? All right, so let me overlap them. The second generate cosine function. You see, first goes up immediately the wave, but now the second source generate maximum and then it goes down. So sine function and cosine function. So over here we have sine function, here we have cosine function. So what's the phase difference between sine and cosine? Pi over 2. Right? So in this case, the inherent phase difference is pi over 2. So in this case, delta phi naught equals to pi over 2. There is no special name, right, for this situation, but the problem will somehow deliver information about this situation. Right? So again, that's what we need to get information about the inherent phase difference for that condition. Again, usually students have no troubles finding the path length difference, and these three situations you just need to remember in order to get information about the inherent phase difference. And again, once you calculate it, and then once you calculate that and then compare, are you going to get this case or that case? If you're getting neither of those cases, it means that you have something in between, not this, neither this nor that. Okay, so now that's what we need, and now let's make a transition to two-dimensional waves. Okay, now let me separate it, or maybe I will just put a big bullet. Right, big bullet. So let me check if I mention everything. Yeah. So now let's make a transition from 1D to two-dimensional case. Basically, from one-dimensional waves to circular waves. Two-dimensional case of circular waves. Circular waves. Right. Okay, so first let's discuss a few things about circular waves. And then transition is trivial. Transition is trivial. So what do we have to do? We just need to replace all those x's with r. I will show what r is, right? And exactly the same condition will be used for circular waves. So what are circular waves? Imagine like pool, big pool or lake. And let's say somewhere in the middle you start creating waves. And you start poking, right, your finger right in water, right, with the same frequency. And of course you will start creating ripples. The ripples will start spreading out from your source, from the source. Right. So those are circular waves. Right. So now first, how can we draw them on a paper or on the board? Of course, obviously, you will have to draw a bunch of circles. The question is, which circles should we use? Because when you look at water, you see circles created by what? First, by crests, sort of kind of bright circles. And then kind of dark circles created by troughs. Which one to use to draw a wave on the board? I think from the psychological point of view, it's better to use bright spots, right? Crests. Any psychologist will suggest something like this, right? So, yeah, so that's what we use. We use collection of crests. We draw circles, right, which represent collections of crests. So, if you have, for example, let me draw first. No, let me use blue. So let's say we have source S1, source 1, right, or on a lake. So you will see, of course, you create circular waves, and now I'm drawing those circles representing this wave. And as I said, these lines are collection of crests. So basically it means that if I start drawing, so it will be, you see, crest on the line. Then between the lines, it goes into a trough. Then again, next to the at the next line, again we have a crest. Then again, between lines, it's a trough, and then again crest. Right? So these lines, collection of crests, are called wave fronts. So these are wave fronts. And underneath I will write collection of crests. So these are crest. And of course, between them, in the middle, between waves, between lines, we have troughs. Right? Okay, so that's what we need to know. And now let's draw the second wave. Right? Second wave, because we're going to discuss interference of circular waves. So the second wave, let's assume that the source is over here somewhere, second source. Now I will have to draw also collection of circles like this, wave fronts of the second wave, circular wave, right? So it will be right. And of course, you remember we're discussing two identical waves. Two identical waves. So amplitude the same, wavelength the same, frequency the same. And this distance between the wave fronts, what is that? It's a wavelength, because what is this? It's a snapshot graphs of circular waves. These are snapshot graphs. Again, that's what you can get with a camera, right? So as a result, this distance between wave fronts are wavelength. Lambdas, lambdas, lambdas. And here the same, lambda, 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 because again, you remember we're discussing identical waves. So this also I can draw crest, trough, crest, trough, crest, trough. And the distance between wave fronts, again here, lambda, lambda. Right. Okay, so now what are R? What is R? So for example, let's say you want to analyze that point, just completely arbitrary point on the surface of water, in terms of, are we going to get constructive interference or destructive interference? Right? So this will be R1, distance from the source to the point in question, and this will be R2. So now if we rewrite this condition, and we were going to have here a delta R will be R2 minus R1. So it's just an additional distance that the second wave has to travel relative to the first wave. Right? So now, after presenting these circular waves, now we can rewrite a condition. And the transition is very simple. As I said, we just need to replace X with R. That's it. So, and that's why we started with one-dimensional case, because it's kind of easier to understand, easier to get through the math, and then transition to two-dimensional case, just replace X with R. That's it. So, and now condition, let me rewrite that. So it will be 2 pi over lambda times delta R plus delta phi naught, and two situations for constructive and destructive interference. M times 2 pi for constructive case, and M plus 1 over 2 pi for a destructive situation. Let me frame it, and that's what we're going to use, because most of the problems are going to be two-dimensional, not one-dimensional. Again, every time delta R, just R2 minus R1. Inherent phase difference we just discussed. And add all this up and see, are you going to get this case or that case? Again, M is an integer.